dear students. Today I will discuss about the application of equal criteria during transients. Now, as I already have mentioned, what is transients? Like if there is certain load change, and that load should be the heavy load. Like if again if there is any fault occurs on the system that creates transient. Now, what how the equal area criteria can be applied to find out the stability during fault conditions, that we will discuss in this lecture. So initially fault is considered for one line in this double circuit line. Double circuit line means two lines are there, you can see from this diagram. Here this is the synchronous generator or alternator which is connected through a double circuit line to the infinite bus. Now already you know what is infinite bus. Infinite bus is the one where voltage and frequency remains constant for all the time, and if you remove one generator from the system or from the bus, that will not affect the frequency and voltage of the system. So that is the infinite bus. Now here this synchronous machine is connected to the infinite bus through the double circuit line. Now when two lines are in working condition, that time what is the power transfer from this side to that side, that we can write from the Parangal equation, which is P pre-fault means before fault EV by X sine delta. So these two lines are having this reactance of XL. So this line is having 2XL, here also 2XL. So what will be the total reactance? The equivalent reactance will be X equals to this one. Means ultimately we will get here XL. Now after fault, this is the post fault. This expression is same, but X is different in this case, because once after fault means when fault is removed, the faulted line is removed from the circuit. At that time only one line will be there, so we will have the reactance of 2XL. So if you can see, before fault, when two lines are in working condition, that time we have lower reactance than the reactance after fault. So actually double circuit line is also helps to reduce the reactance of the line. Now actually here in the next slide we can see this the initial power angle curve is this one, where this power is more maximum power EV by X sine delta. Now why? Because X is less here, that's why this pre-fault power will be more, but post-fault power will be less because X is more, the denominator is more. So if you can see the curve, this represents the pre-fault curve and this represents the post-fault curve. Now, and this is the curve, this is during fault. During fault what happens? The reactance becomes very high, that's why the power is reduced. And how that reactance becomes high, that I will share you the image of the some calculation. You can go through it to see during fault what will be the power flowing from sending end side to the receiving end side, or from this generator to the infinite bus. So under normal condition, as P delta curve is shown by this curve A, this is pre-fault condition. So and our mechanical power is P1. So this is the delta 1 is the initial operating angle. Now what happens when fault occurs? During that condition, the power reduces. That's why the curve is shown by curve V. This is during fault. So if you can see our now working this curve is this one during fault condition. So as mechanical power is this much and electrical power is this much, and mechanical power is more than the electrical power, the generator will accelerate. So accelerate till when? Suppose uh, accelerate during acceleration, the angle delta is increasing from delta 1 to delta 2, and at that instant the circuit breaker which is connected in the system, you can see the diagram. I'll show you, let me. These are the circuit breakers. This are the circuit breakers. This circuit breakers will disconnect the line from the system. So at delta 2. So what happens? The P delta curve power becomes more than during fault condition. Therefore, this will be the curve after fault. So this C is the post fault curve. Now what happens? Due to the accelerating power, the angle is increases from delta 1 to delta 2. Now at that point we can see our curve is this one, the post fault curve, because circuit breaker removes the circuit or removes the faulted line. So at this point, if you see, as delta increases, so power will also increase. Now electrical power will increase. So if you see, electrical power is increasing, and why the delta is increasing? Delta is increasing due to the accelerating power that I already have told you in the previous class. So as delta is increasing, electrical power will also increase. So we can see after this point the deceleration starts, but due to the kinetic energy stored in the machine during acceleration, that will further increase the load angle delta. So suppose this delta is increasing till this delta 3. Now at that instant the accelerating area becomes equals to the deaccelerating area. So this area and this area will cancel each other. Now why this is accelerating area? Because at this instant acceleration takes place, and this is deaccelerating area A2, because at this instant deaccelerating takes place, but action will not be seen. When these two areas are equal, they will cancel each other, then there will be no effect of accelerating force. So at that instant again the delta will now reduce. Why? Because as deceleration effects we can see from this point, so delta will reduce in this way. Now this actually what happens, suppose our A2 is very much more than, sorry, A1 is very much high or higher than this A2. That time what happens, if the accelerating area or accelerating energy is much high, means that energy will accelerate the machine until this becomes equals to this A2. Suppose we do not have any option or any space here where A1 becomes equals to A2, like A1 is always greater than the A2, that times what happen, machine will accelerate and machine will angle will increase and increase. Till that point also we are not able to balance accelerating energy to the deaccelerating energy. Therefore after crossing this point the electrical power again becomes less than the mechanical input, so machine will start accelerating again. It will not get that point where that A1 is equals to A2, means deaccelerating effect can't be seen. because accelerate after that point there is no chance to make P1 means mechanical power is equals to electrical power. So this is the time, actually this is the that angle where after which it's not possible to get or make A1 is equals to A2, therefore machine will lose its stability. Why? Because the angle will increase and increase, the load angle will increase and increase, it will not able to balance the electrical power with the mechanical power. That's why machine will lose its stability. Now if you see, this is the delta critical, means this is the actually limit of the increase in delta, limit of the delta till which we can go. After that is not possible to make synchronism between the machine and the system. So machine will lose its synchronous stability. So this is called actually delta critical angle after which is not possible, and this portion is called A margin. A margin means initially I said at this instant this A1 becomes equals to A2, accelerating energy becomes equals to decelerating energy. Therefore, this is the portion that we have for transient stability margin, because we if this is more than this A2, then we have the option to go till this. So this becomes the transient stability margin for this system. So this is the application of equal criteria during fault condition, and here everything is written. Please go through it. If you have any doubt, you can ask me. And see here, delta critical is the limit of transient stability, because after which it's not possible for the machine to get the stable condition. And A margin is the margin between is the area between delta 3 and delta critical. If you see here, delta 3 and delta critical, this area represents the A margin. This is the transient stability margin or transient stability limit of the system. Now what is transient stability limit and what is stability limit? These definitions are given here. Stability limit is the maximum power that can be transferred from a source to the loads, or source synchronous, in this case synchronous machine, to the infinite bars without loss of synchronism. That power, that maximum power which can be safely transferred from the source to the load. And steady state limit is the same thing, the maximum power that can be safely transferred from the source to the load without the system becoming unstable. And the example for this, actually if we gradually increase the load under steady state condition, that becomes steady state stability. Therefore steady state limit is the maximum power that can be transferred without the system becoming unstable when the load is increased gradually under steady state condition. Same way, transient stability limit is the maximum power that can be transferred without the system becoming unstable when there is a sudden or large disturbance occurs. So as I said, transient stability actually large is created by large disturbance. Therefore, this here large and after large disturbance or during large disturbance, if the system has the ability, then it's called transient stability.